Hi, good morning to another episode of EV Fundamentals. And today I will talk about field-oriented control. To give you a bit of context, open inverter software so far hadn't used field-oriented control because asynchronous motors can be controlled much simpler and without taking current sensors into account. By just pretty much fixed voltage hertz curve and just appropriate slip. With synchronous motors you could in theory do that as well. In practice you cannot. So the reason for that is that they are permanent magnets and the motor will generate a voltage as you turn it, which in a synchronous motor does not. So there's a very fine line between generating positive or negative torque, also called regen. And it's just virtually impossible to be on the right side of that line with just feed-forward methods. So current control is definitely necessary. Okay, just quick fundamentals of field-oriented control. The basis here is we're looking at a 4-pole rotor now. So every angle has to be multiplied by 2 electrically. Yes, so we have the Q-axis. So if the rotor magnetic field is here in the Q-axis, it will generate maximum magnetic torque. And then here we have the D-axis. And if the rotor magnetic field is at the D-axis, we will not generate any torque at all. And in addition, for interior permanent magnet motors, if the magnetic field is in between those two, we will be generating what's called reluctance torque. And that's basically generated because the missing iron is trying to line up with the stator magnetic field. So we have 2 torque components. And that's important to know because more traditional synchronous motors with magnets stuck to the outside of the rotor only have magnetic torque, so this D component is always 0. In our case, it's not. Let's take a look at the very generic structure. And I think I will be switching back and forth between the code and this, so we see where we are. So where do we start? Let's start at the motor. So here, green line. So the motor is turning, and it generates currents, or currents go into the motor. And we measure these currents. In fact, it's efficient to only measure 2 because the third one is just linearly dependent on the other 2. Then we do what's called here in this case we have the traditional 3-phase sine wave pattern. Then we do what's called a Clark transformation, which transforms it to a 2-phase system. So here you can see 2 sine waves offset by 90 degrees, and that is already like the D and Q components, as sort of just in a rotating frame. Okay, and next we do a Park transformation, and that transforms those sine waves to DC quantities. And that's of course very useful, because now in this box right here, we can just do traditional current control, like a lab power supply in current control mode would do. It just increases the voltage until it hits its regulation or its control target. And that's all we do. Yes. So yes, current in, voltage command comes out. And then it goes, inversely back. We generate the 2-phase sine system first, then we go through the inverse Clark and generate a 3-phase sine wave. Then we do space vector modulation to have more usable amplitude. And then gate drive and inverter and all that. And well, we come back at the motor. And then it all starts over in an infinite loop. Yeah, that is our control structure, and so I will spend most time going over the code, because that has some, well, maybe surprising or not obvious at first sight tricks to it. Yes, so this is the main control method. I will increase the size for you if you're watching on tablet, phone. So the first thing we do is get the rotor angle. And in our diagram, that's basically this part right here. So rotor angle is very important, obviously, because that lets us align our field to the correct D and Q component. If there's any offset here, we will be thinking that we are creating a D component, but actually there's a bit of Q component in there, and the whole system is not going to work. Yes, so update rotor angle has actually the first practical surprising thing in it. So let's go and take a look. No, sorry, no, it does not. Calc next angle sync, that's what has the surprise in it. So, pole pairs, like said, most motors have more than one pole pair, even though multiple pole pair versions exist. Single pole pair versions exist. So for us, it's important the ratio of pole pairs between the resolver, or the position feedback, and the actual motor. And in most cases, that is equal. So if you have like a 4-pole pair synchronous motor, they will stick a 4-pole pair resolver to it. So this equation completely cancels out and becomes 1. Okay, synchronous offset. So basically, let's see if this picture could be helpful. Ideally, the resolver would, oh, why is this gray? Oh, so we can see it. The resolver would report a 90-degree angle when the rotor is at this position. But in practice it will not. It will maybe report 95 degrees or... Anyway, there's going to be some offset between what the resolver reports and where the rotor is actually at. So that's a parameter that we have to tune to get this correct. Yes, then we get the supposed rotor angle. And now here comes another surprise. It's parameter sync advance. So by the time we run through this routine, the angle that we obtained here has a certain age. It's not measured at that instant, but it has been measured some time ago. In this case, I think it's about 60 microseconds ago. So yeah, in that time the rotor will have moved on and is actually at a different position. And of course, the faster the rotor spins, the more it will have offset from the measured position. So to compensate for that, we have this sync advance that we multiply with the current rotor frequency. Yes, and then we all tie it all together. The measured rotor angle plus the modified sync offset to get the real mode rotor angle. Yeah, and that's pretty much it in here. So, next, another surprise. So ignore the filtering for now. But we see we generate here a modded Ki, and Ki is the integral gain of our PI regulator. For now, I'm assuming you know what a PI regulator is. So basically, this regulator has to be quite dynamic, because to generate, say, 100 amps at a low frequency takes less voltage than generating 100 amps at a high frequency. And the integrator in our PI regulator has to make up for this difference. And in order to make it easier for the integrator, or to force less integrator wind up, we increase the integral gain with rotor speed. Just gives us a better, faster response. Yeah, and then finally here we are in process currents. So process currents does this part down here. It obtains the currents from the current sensors, and it does the Clark and Park transformation. And the function returns already with the direct and quadrature current values. Okay, and then we have another practical detail, which is field weakening. So obviously at some point the PI controllers will run out of voltage to generate, to maintain the requested quadrature current. So what we do in this case, we weaken the rotor magnetic field, and thereby we reduce the back EMF, like the voltage that is generated by the spinning rotor, and thereby we generate more room for quadrature current. Yeah, so basically this is another controller that tries to reach the control target for the quadrature current. So if the actual Q controller, that one, maxes out, this controller will step into action and do the field weakening, so we still are able to reach our target here. And at this point, I'll be honest with you, this isn't working 100% yet. Like, it does work for acceleration, but if you're stepping into regen in the far up in the field weakening region, there's still some overcurrent trips going on, and yeah, it still needs to be worked on. But in principle, this should be how it works. Yeah, we are skipping the test code. Yes, so now we have, so yeah, this field weakening controller adds to the control target of our D controller, because D current weakens the field. Yeah, so we run our D controller, and then we look how much voltage is left to generate quadrature current. So obviously the D controller has priority over the Q controller. We see how much amplitude is left, and we limit the control output by that, and then we run the actual Q controller. Yes, so that's basically, yeah, this box right here. And then we go back, inverse Park and Clark, inverse Park, inverse Clark. And also the space vector modulation is also in this function call right here. Calculate a few values, and then we shift the normalized duty cycles into a region that's appropriate for our timer hardware. And then we transfer this to the PWM registers. And here you see another implementation detail. Because for fog everything needs to be lined up. So the PWM channel 1, let's go into the graphics. PWM channel A has to generate current A, and PWM channel B has to generate current B. And yeah, if these are not lined up, fog will not work, we'll get confused and usually trip out with overcurrent. So, since, well, I messed this up on the Leaf adapter board, I swapped PWM channels 1 and 3. I introduced a parameter to swap this back in software. Yeah, so this is the basic control structure of field-oriented control. And now let's look at one addition for interior permanent magnet motors. So, like I said, there is a magnetic torque that's generated by this axis, and there is reluctance torque that is generated by a magnetic field coming from this axis. And there is an optimum, like which torque component gives you the most total torque per current that you put into the stator. Yeah, and to calculate that, there is the most torque per amp method. And I've stolen that from, I think, a TI paper. So that's what I want to look at. So we want to generate some total current, and this function has the task to split this current into a magnetic and reluctance torque. Yeah, so there's some complicated formula, and this formula contains motor-specific parameters. So you would think that, yeah, I do measure these parameters, but I do not. What I did is I took some very typical parameters, I think from a previous synchronous motor, and put them into an OpenOffice calc sheet. And then I varied these parameters and looked how much this distribution would change. And it turns out it's not so much, so I thought I'll just stick with those parameters and just assume they won't vary too much between different motors. Yeah, and what also helps is that we're not actually using, for example, the absolute value of the quadrature inductance and direct inductance, but we are using the difference between them. So that eliminates even more differences between different motors. Yeah, so in the end we have like a reference for our direct and quadrature current, and this is passed back to the calling function. Yeah, that's all that MTPA is. Thanks TI for writing it up. Yeah, we can take a quick look at the actual transformation functions. Maybe good to have seen them. So here we enter the Park and Clark transformation function with the measured physical quantities in amps. Because if we use physical quantities here, we can also use physical quantities for configuration, as in how much current do we want to go into the motor. Yeah, so transformation needs the sine and cosine of the current rotor angle. And then here we have the transformation from 3-phase, 2-phase, the I alpha and beta current. And then here we have the rotary transformation from alpha beta to D and Q. Yeah, I think that's pretty simple code. Not many surprises here. 6 lines of code, that's all there is to it. Yeah, and maybe the limit function is sort of interesting. So basically what we have here is like a triangular thing. So the total voltage we allow is, for example, 40,000 digits, and that's this part of a triangle, and we have already used this much for D voltage, and now we need to calculate how much is left for Q voltage. So it's like the usual Pythagoras formula, where we subtract the square of the D voltage from the maximum possible voltage and take the square root. Interesting part here is that we do take a square root, and I've implemented a what's it called again? Oh, I haven't commented it. A Newton iteration to calculate square root. So I've optimized this a bit. You can see up here I've optimized the starting value, and usually within, I think, like 4 iterations it will have arrived at the square root, so it doesn't take long at all. Yeah, so this saves a lot of lookup table stuff. Okay, and finally we have the inverse Park and Clark transformation. Again, we are calculating the sine and cosine again. More optimized version save these sine and cosine values because they are the same used in the forward transformation. But I mean, this is just a table lookup, so I couldn't be bothered to optimize that. Yeah, and then we go back from dq to alpha beta. Some simple multiplications and subtraction and so on. And then we go from alpha beta to 3-phase again. Calculate some duty cycles. And the domain of these duty cycles is 16-bit. So minus 2 to the power of 15 to plus 2 to the power of 15. Yes, and with that we calculate the space vector thingy. That's sorry for the mess. So this part right here, and you can see this gives us some extra amplitude, usable amplitude up here. Yeah, and we calculate, this is actually old code, same is done in the sine, in the pure sine implementation. Yeah, and we shift it up. We convert the negative values to positive right here, and we do some short pulse suppression. That's also all old code. And yeah, that is pretty much there is to it. So to round it off, let's take a look at how it actually behaves in practice. So I know this is a bit convoluted. Am I still painting gray? No, not green. Weird. So yeah, what we see here, this this orange color right here is our frequency, rotor frequency. The red and blue is our D and Q currents, and the purple and yellow is our D and Q voltages. So now we can see how the controllers generate the voltages to obtain their control target. So at this point right here we can see some acceleration starting. So we see the frequency rise. We see the D and Q current are at some constant value, but the D and Q voltage is not constant. It has a slope, and that's because, like I said, the required voltage to obtain the current is frequency dependent. Yeah, and then here we see some miscellaneous driving with regen and acceleration. And at the end I made another test run to see the switch from acceleration to regen, and that also has an interesting detail. So yeah, here we see another acceleration as denoted by the quick rise in frequency. And again we can see pretty much constant current values. And we can see the voltage values as they rise with frequency to maintain the current. Now, at this point, I seem to have stopped. Oh, very good at drawing straight lines. I seem to have stopped accelerating and went straight into regen. And now we can see something interesting. Obviously, the quadrature current drops below 0 because that's what regen is. Negative torque. and the direct current stays below 0. The magnitude is a bit less, but it stays below 0. But the direct voltage shoots up and becomes positive. And it loses a bit of its frequency dependence. There's still some left, but it's not as much as in the accelerating scenario. And this is just an observation I made. Unfortunately, I can't explain it. But for this reason, this is why your PI controllers need to be really, really dynamic to make this transition from negative to far into the positive really quickly. Because otherwise it will create current transients and they will usually trip one of the overcurrent mechanisms. Yeah. So, I think that's it for now. I hope this can add to the various fog tutorials out there, give you some practical insight. So yeah, I hope you found this interesting, and if you do, thumbs up, leave a like, it's the same. And yeah, also let me know if what topics would be interesting to you to cover in some future episode of EV Fundamentals. Thanks for watching. See you next time. Bye bye.